We first look at the free propagator for the Hamiltonian which has no interaction, so we just keep H naught, where psi naught is a non-interacting ground state. The field operator phi depends both on space and time. So we need to time evolve the expression for the field operator in the position x. If there is no external potential, we only have the kinetic energy, and in this case the phi I naught will just be the plane waves we worked out before. The time component is carried by the evolution operator with the h naught free Hamiltonian. And because of the time ordering product, we have two components, one with phi phi dagger and one with phi dagger phi. We see that the first term creates a particle on top of the ground state, propagate it, and then annihilate it later. The second term, on the contrary, first annihilate the particle, which is already in the ground state, and then recreate it later. So the first term describes the propagation of a particle, the second term describes the propagation of a whole. Both are physically relevant and could happen. For simplicity, however, we are going to focus only on the particle term, the first one, and we are not going to take into account the whole propagation. We now use the fact that psi naught is a ground state of h naught, and therefore we can just replace h naught by the energy of the ground state. A dagger creates a particle with an energy E0J. The new state is again an eigenstate of h naught, but this time with the energy of the ground state plus the energy of the new particle. We see that if we create a particle and annihilate another one, not in the same state, then we will have a new state which will be orthogonal to the ground state. That will be a particle Hall excitation of the ground state, and therefore the expectation value of A dagger will be 0. The only way this can be non-zero is if we create and annihilate exactly the same particle, or the particle in the same state. It will be more convenient to have the free propagator in the energy domain, and for that we need to do a time Fourier transform of the propagator. So we need to take the Fourier transform of a theta function times an exponential function. This form for the one particle propagator is quite general. It involves the single particle eigenstate at different positions in space, as well as their energy in the denominator. So we got this propagator for a free Hamiltonian. The propagator for the Hamiltonian with an interaction has the same form. But now the single particle states and their energy are unknown because they have been modified due to the interaction term. Our next step will be to find an equation for the propagator, which we will then be able to turn into an equation which will allow us to get this single particle states as well as their corresponding energies.